In this video, I'm going to show you how to use Lagrangian mechanics to analyze a system consisting of a pendulum and an accelerated reference frame. Specifically, I've set it up as a pendulum on a cart accelerating in the positive x direction. Now the main coordinate here that's of interest will be this angle theta. So if we look back on this cart, while the cart's accelerating that way, the pendulum will be oscillating back and forth. And so if we zoom in on the pendulum, we can see it'll be oscillating back and forth like this. And the motion will be characterized, therefore, by this angle theta. So the way I've set up the coordinates in this problem is such that it starts, as far as x position goes, at x equals 0. And it's accelerating with a constant acceleration in the positive x direction. And the 0 of the y-axis is right at the top of the pendulum bar. So with that in mind, we can write out the displacements and get ready to do Lagrangian mechanics. Okay, so we've got two contributions to the x displacement. First, the cart's accelerating in the positive x direction, so kinematics tells us there will be a contribution to the x displacement with the value v0, the initial velocity, times t plus a half a0, the constant acceleration I told you about earlier, times t squared. But of course, the pendulum is also oscillating back and forth, so there will be a contribution to the x displacement from that. Now we can go over to this diagram here and use some simple trigonometry recognizing the right triangle to figure out what that x displacement is going to be as a result of the pendulum oscillation, and unsurprisingly it's just L sine theta. Now the only contribution to the y displacement will be this oscillation because, well, it's not accelerating. The cart itself isn't accelerating in the y direction at all, just in the positive x direction. Now, since I selected the y-axis to begin right here, or to have it 0 right at the level of the top of the pendulum there, the value of the y displacement using similar trigonometry is simply negative L cosine theta. And that's using trigonometry similar to the trigonometry used to figure out the oscillation contribution to the x displacement. Now from here we can simply use the chain rule here for these terms to take the time derivative of the x and the y displacement. With that, we can come over here and start working out what the kinetic energy is. Of course, we've got kinetic energy for the motion in the x direction and kinetic energy for the motion in the y direction. So then we can insert these values we computed for x dot and y dot into it, and we get this immediately. Doing a bunch of squaring and some simplification, we ultimately work our way down to here. Now, of course, we're interested in the kinetic energy because the Lagrangian, which is going to be used to make our problem radically easier, Lagrangian mechanics, as I said in the beginning, the Lagrangian is T minus U, where T is the kinetic energy and U is the potential energy. So we need this value for the kinetic energy. It's quite important. So then, continuing on. Of course, the only potential energy here is gravitational potential energy, which is just in the downwards y direction. So, of course, the potential energy is going to be mgy, and we worked out the value for y using trigonometry up here, just negative L cosine theta. So then, unsurprisingly, the gravitational potential energy here, and in this problem, the whole potential energy is just negative mg L cosine theta. So then if we subtract that potential energy from the kinetic energy, we arrive at the Lagrangian, which is this whole thing in the box. Somewhat long and complicated, and it may not seem obvious why this is simplifying the problem, but trust me, doing this with Newton's laws is quite a bit more obnoxious. Anyway, to get the equations of motion, of course, the first thing we need to do is evaluate the derivative of the Lagrangian with respect to theta. Now, this is directly doing the derivative, and then simplifying a little bit by factoring some things out and canceling this factor of 2 against the half, we arrive at this result, which I've boxed down here, the final result for that derivative. Okay, so then the next thing we need for the Euler-Lagrange equations, of course, is the time derivative of the derivative of the Lagrangian with respect to theta dot. So then I did this inner derivative first and just set the time derivative out here. It works out like that. Then we can use the product rule and the chain rule to take the time derivative of this. It works out to this value that's boxed. Now then we need to set these two boxed values equal to each other, or equivalently set the difference between the two equal to 0. That's just the Euler-Lagrange equations of motion. Doing that gives us this messy thing, which conveniently simplifies down quite a lot, down to finally this result, which we can then rearrange to yield this final simplified equation of motion. This is one of the main products of this video, to show you how to get to these equations of motion for this system using Lagrangian mechanics. So this bolded boxed result, that is one of two primary results. But we're also going to analyze the system. We're going to look for the equilibrium angle. Now, typically, the stable equilibrium angle for a pendulum, and if you're not letting it go to very high angles, then the only equilibrium angle is theta equals 0. And so we would expect that if it's accelerating in the positive x direction, that acceleration is going to, in effect, shift the gravity field, such that the equilibrium is in a slightly moved backwards angle. So we want to figure out exactly what that angle is. And then we also want to confirm that if we take the acceleration a0, the constant acceleration in the x direction of the sled, or the cart, if we let that go to 0, we want to see that the equilibrium angle also goes to 0. Of course, at equilibrium, the acceleration, the angular acceleration goes to 0, so theta dot dot equals 0. That yields this equation for the equilibrium angle. Manipulating that, we get this relation here. So we notice a few things. One, if a0 goes to 0, the tangent of the angle equals 0, which is satisfied appropriately by theta equilibrium equaling 0, so it does do that. And also, if a0 is not equal to 0, it does in fact shift the angle, exactly as you'd expect. It moves it back a little bit so that it's oscillating around a new equilibrium. Specifically, the tangent of the angle, the equilibrium angle, is negative the acceleration over the acceleration of gravity. So it all makes intuitive physical sense. And this idea of this acceleration shifting the gravity field, simulating like another contribution to the gravity field, that is very much in the theme of the equivalence principle. It is sort of simulating a shifted gravity field. And of course the equivalence principle is famous for its role in general relativity, so this problem is really quite a cool one to do. Dietrich out.